I hope everybody can hear me. This is Drew Ellsbury, Regional Sales Manager at Heat Pipe Technology. I appreciate you all joining us today for the wonderful world of dehumidification heat pipes. Before I begin, if I could ask a few people to go into the chat screen and just let me know they can hear me okay. All right, I got a few positive answers here. So again, thank you all for joining. If you were with us last month, you will recall that we talked specifically about the heat recovery side of the heat pipe house. Today we're going to dive into the dehumidification side, or what we, what's commonly known as the wraparound, which many of you, if not most of you or all of you, know that is what we invented some 30 plus years ago and were founded on by a company. So we're going to dive into the wraparound heat pipe and pretty much everything, hopefully, well, not everything, but a lot of good stuff to know. So what am I going to cover? I assume most people, if not all people, know how the heat pipe in general works, but I've learned over the years that assuming can get me in trouble, so we're going to talk about it. We're going to talk about the energy code, or 90.1, but also the building code that's typically tied into that. We're going to talk about the controllability of a wraparound heat pipe, which is a specialty here at HPT, and not just what it is, but how to best use it. And then a new metric that's out there, or that's coming actually, called MRE. It's actually from a standard that's coming soon, so we'll talk about that. And then, of course, case studies. So that right there is a basic heat pipe. As it's known today, it's simply a tube. It's got refrigerant in it. If there's no delta T, refrigerant's just going to sit there. But as soon as you apply heat to one side, that side of the heat pipe, or that refrigerant, is going to pick up that heat. It's going to boil, and then you're going to create a pressure differential within the heat pipe, and that vapor is going to move all by itself to the other end, where it'll give off the heat to the cooler airstream, and then that vapor turns back to a liquid, and it's going to go to the other side, pick up the heat, turn to a vapor, go back to the other side, and it's going to keep working all by itself. All you need is a delta T, you create a delta P, and that's the driving force within a heat pipe. Now that's what we call a single tube type circuit, where you've simply got a single tube. We use what we call a loop circuit. So instead of the liquid and the vapor traveling within the same diameter tube, battling forces, let's say, we've got the liquid going one way and the vapor going the other way, but all traveling within kind of in the same direction, like a racetrack, like you see here. So in this scene, you've got the hot side on the right side. So if there was no delta T, you just have liquid refrigerant sitting at the bottom of the loop there. As soon as you apply heat on the right side, that liquid's going to pick up the heat. Vapor, it's going to go up that loop and around to the other side, give off the heat, condense to liquid, and it's going to keep moving in an oval like it's on a racetrack. So a lot of those single tube circuits that are still out there today are using big 1-inch aluminum tubes. We're able to use 1/2-inch copper tubes. That allows us to take up less space, get a little bit better performance, add less static pressure to the system, and it allows us to do. So we take that concept and apply it to what we call a wraparound heat pipe. So if it were just basic energy recovery, we would put one end on the hot side here and take this 80-degree air, pick up the heat with the refrigerant. It's going to boil, but it's going to go to another airstream and just dump off that heat. In this case, we're wrapping that heat pipe around the cooling coil so that we can use that heat as free reheat. So as you can see here, we're not only pre-cooling that air before it enters the cooling coil, which is going to, of course, reduce the load on that cooling coil, but we're also giving you the free reheat as well. And that's really the key to the wraparound heat pipe. If you just want to pre-cool, then just do heat recovery. But if you are controlling humidity by using reheat, then the wraparound heat pipe is your answer, because it's not just giving you reheat for free, it's pre-cooling that air to do it. So you're doubling up your BTU efforts, so to speak. So now we're going to look at a site chart, because let's face it, no fun webinars complete without a site chart. So if we did not have a wraparound heat pipe and you needed to get from 80-degree air down to 50-degree air off the cooling coil, you would have to go all the way from point A through point B all the way to point C, and that's how much coil you need, so to speak. The heat pipe, which is a sensible recovery device, we're going to pre-cool that sensible heat and in essence allow that cooling coil to not work as hard. So the pre-cool side of the wraparound heat pipe will pre-cool from point A down to point B. And now, as you can see, you need a smaller coil because you only have to get from point B to point C. And then, of course, the heat that was recovered from A to B is then therefore just wrapped around the cooling coil and added as reheat from point C to point D. Now, the other way you could do this is if you used the same size coil as before. Instead of going down to a 50-degree dew point, now that coil can handle more latent capacity and drive that dew point down even further as it's able to ride the saturation line a lot further. And I'd also like to point out that the dehumidification heat pipe, it's commonly known as the wraparound heat pipe, but we have the model number DHP. So when you see DHP, know that that is the dehumidification heat pipe or the wraparound heat pipe as shown at the top there. So one application that it can be immediately used, and it's very often used, is to meet energy code or building code. So 90.1, and it's going to tell you that depending on where you are in the country or what climate zone you're in, depending on how much outside air you're bringing in and how much percentage of your total airflow is outside air, it's going to tell you that you have to have energy recovery that's able to recover at least half of the total enthalpy that's available. Now, there's certainly ways to do that. A lot of them can get expensive, but there are also some exceptions to that requirement. There are several, but the one I want to focus on, of course, is the one in bold there that simply states if energy recovery in series has its qualification, then you don't have to do anything else to meet this code requirement. So basically, energy recovery in series, what is that? I mean, that's what a wraparound heat pipe is doing. We're recovering heat on one side of the cooling coil and in the same series of airflow, redistributing that heat as reheat. So basically, if you use a wraparound heat pipe, you have met code and don't have to do anything else. So know that, one, if you're doing it already, you don't have to do anything else. You've met code. Or if you're having a very difficult time, whether it be from design standpoint or from a cost standpoint of meeting that code, by simply putting a wraparound heat pipe in the air handler will allow you to meet code. So something to keep in mind, that the wraparound heat pipe is a code allowance and an exception to that 50% rule. So let's talk about controllable wraparound heat pipes, because that is something that's one of our bread and butters that you don't get everywhere else with some other heat pipes. So I really want to talk about what it is, some of the details, and then how best to utilize them. So first of all, know that when we're talking about a controllable heat pipe, we are typically using solenoid valves. So we're basically installing these solenoid valves in each circuit and shutting them off and opening them back up as needed and staging them together as needed for the BAS, and we'll get into that as well. These solenoid valves can be either 24 volt or 120 volt, and that voltage is really based on the number or quantity of valves. 24 valves are going to stay at 24 volts. When we go up past 24 valves, we're going to go to 120 because the wiring just gets too big. But that's the difference between the 24 volt and the 120 volt. And when we stage them together in 3 or 4 stages, and of course the more stages you have, the better control you're going to get. So here's a picture of a wraparound heat pipe with some solenoid valves in them. I'm going to ask a question here that unfortunately no one is going to be able to answer out loud for me to hear, but I'm going to ask it just to get you thinking. Can anybody tell me by looking at this which direction the air is flowing? Is it going left to right or right to left? So take a look at that, think about it for a second. And if you said right to left, then you are correct. And I'm going to assume that everybody said that because, of course, everybody knows this. Of course, the question is why. Well, the reason is because that piping up towards the reheat, up that heat, that refrigerant is going to boil, turn into a vapor, and we want that vapor to go up. And then, more importantly, when it gives off that heat and condenses back to a liquid, it's nice to have that liquid slope down. So when thinking about that, one question we get sometimes is, what's the wraparound heat pipe doing during heating mode? Is it working against you? The answer is no. When we're in heating mode, first of all, now you've got cold air entering, and that liquid refrigerant is just going to sit at the bottom there, and it's not going to go up anyway. But also, and more importantly, typically that cooling coil is not going to be on during heating mode, and if it's not on, there's no delta T. And without a delta T, we're not going to do anything. Now, when we get into larger systems or circuits, and when we get into a lot of circuits where there's going to be a lot of solenoid valves, it gets to a point from an ownership standpoint that it no longer makes sense. And then we do something a little bit differently. We actually are able to use modulating valves, but we have to use a different heat pipe, what we call our DHPV here. For those familiar with our HRMV, or our split passive heat recovery module, except now we've wrapped it around the cooling coil. So in this case, we've taken every 2 rows as its own circuit. So what you're seeing there is a 2-row wraparound heat pipe where you've got vertical tubes in this case being tied into common headers. Because the good thing is that allows us to use much fewer valves, and we're talking modulating valves now that can modulate that heat recovery versus just staging it. The downside here is that you do lose a little bit of performance, because by pulling many circuits into common headers is going to lose some performance for you. So we only go this route. We like to capitalize on the performance of the wraparound as much as possible. So we're only going to go this route when it certainly calls for it. So that's what we do. But the big question is why? Why would we even use a controllable heat pipe? Surely it's going to cost a little bit more than a regular heat pipe. That's a fair guess and a correct one. Well, the easy answer is that you can control or maintain a set point without overheating. If you're not controlling the heat pipe and it's simply driven by delta T, then if the cooling coil is supplying the same temperature off the coil all the time, but the entering air gets warmer and warmer, that means the delta T is getting bigger, and we're recovering more heat and therefore providing more reheat. And you might come to a point where you don't want all that reheat. If you don't have control valves, then you're just going to have too hot of air that you're going to have to do something else to overcome. But if you put control valves on it, then you can stage off a circuit to get that heat down, and if it's still too hot, stage off another circuit until you get it down to that set point that you need. So take a quick look here. Here's a scenario I ran in Jacksonville, 10,000 CFM unit. We're going to assume that there's 50-degree air coming off the cooling coil, and the maximum allowable leaving air temperature out of the air handler for this design is, let's just say, 65 degrees. So we don't want the air to get any hotter than that. And we'll look at payback and stuff, so we'll use some local utility rates in Jacksonville, but these can certainly be applied to anywhere. So if we took just a 2-row, as you can see, 2-row gives you anywhere between 8 and 15 degrees based on that overall delta T. In this case, yeah, we're pre-cooling and reheating a little over 13 degrees or so. So that's great. You know, now we're heating it up to 63.5 degrees. But yeah, if we want to get up to 65, well then we're underperforming. And yes, you could leave it as is. You're never going to get too hot, and you're never going to have to worry about controlling it, and you are good to go. But if your focus is to save as much energy as possible, well then you're underperforming because you're not taking advantage of the fact that you can reheat up to 65 degrees all the time. So how do you get up to 65 degrees? You add more rows. So what do we do if we go up to a 4-row wraparound heat pipe? Well, obviously, you add more rows, you're going to recover more heat both on the pre-cool side and therefore on the reheat side. So you can see that instead of reheating and pre-cooling by 13 plus degrees, now we're doing it 20 plus degrees, and obviously that is too hot. So if you need to get to 65 on these peak days, well, now it's too hot. So what do? You add control valves. So now on these peak days, you shut off a circuit and it's going to back it down to 65 degrees, or if that's still too hot, then you stage off another circuit, and so on, so that you're capitalizing on the allowable reheat as often as possible to maximize the energy savings at all times. So a better way to look at it, instead of just controlling to a set point, is actually sizing the heat pipe for part load performance. Because if, according to ASHRAE, you know, that peak day is 1% of the time. Now, whether it's 1%, 2%, 5%, 10% of the time, regardless, it's a small percentage of the overall time. So, like anything, I mean, you hear this argument on the, you know, chiller side and other equipment all the time. Why size it for the time where you're spending the least? Why size it for those part load days where you're spending most of your time? Get as much performance as you can, and then on those peak days, just start shutting off circuits so you don't overheat the space, but you're always maximizing your performance. So if we take that same example, look at that 2-row non-controllable, again, we were able to heat that up to 63 plus degrees. It's never overheating. We'll budget that at, say, $1 a CFM, and if we ran Jacksonville weather bins for 24/7, 365 at those utility rates shown below, we would see that this heat pipe is going to save a little over $8,200 for a year, and obviously that's a very quick payback if you spent $10,000 on it. And that's great savings, nothing wrong with that. But if you want to capitalize and optimize your savings, then not just add the rows, but make it controllable so you don't get too hot on those peak days. And first thing I want you to notice is that before, when we did four rows and non-controllable, we were heating up to a little over 70 degrees. When you add control valves, you're essentially adding friction to the heat pipe and the refrigerant circuit. So friction means energy loss, so therefore that energy is going somewhere else. So instead of capturing all those BTUs, we lose a little bit of performance. So now instead of 20 degrees, we're getting almost 18 degrees of pre-cool and reheat. But we're still too hot on those peak days, so we're going to have to shut off some circuits on the very hot days. But at the rest of the time, you are getting more BTUs than you would have if you had less rows. So yeah, it adds twice as much static, which means twice as much fan energy. And yes, it's going to cost more. In this case, doubling the amount of rows and adding valves is basically going to double the price of the heat pipe. But the savings are obviously going to be much better to maximize your BTU savings. So now instead of $8,000 a year, you save $10,500 a year. And your payback, even though you paid twice as much for it, is still less than 2 years. And once you've paid that off in less than 2 years, you're going to save over $2,000 more per year. So if you want to look at it from the premium for the heat pipe, you've now paid $10,000 more to save over $2,000 more per year. And that's the real key here is, yeah, you are paying a premium, but you're paying a premium anyway for energy recovery. So if you're going to, you might as well maximize those savings you can get, and doing it this way allows you to do that. But I'm going to take it one step further. and talk about partial control. So let's say that at some point on that design, they might need 50-degree air delivered to the space. If that's the case, then yes, you would want to put control valves on every circuit so that at some point you have the ability to completely shut off the heat pipe and deliver that 50-degree air. But let's say that it's really designed for 55-degree air minimum or something like that. And that means you're always going to need some reheat. If you're always going to need some reheat, then why put valves on every circuit? Why not just put valves on enough circuits to shave the load, to shave that extra reheat on the peak days, but always get you that, let's just say, 5 degrees of reheat at all times? Well, now you've truly optimized the system. So taking it a step further, first of all, if we made it 50% controllable, now we've got half as many valves on there. If you've got half as many valves, you've got half as much friction loss. So you've got, give or take, half as much of a performance hit, let's say. So now you're actually going to get even more BTUs all the time. You're still adding the same amount of static because it's still 4 rows, but because you're adding half as many valves, it's not going to cost as much. You don't pay for those extra valves that you didn't need in the first place. So it's going to cost less. It's going to save more. So now your lead time is going to be, or your payback, excuse me, is going to be even quicker, and you've truly optimized the system. So I would recommend anytime you're considering using a wraparound heat pipe, and the focus, which it should be, but is to save as much energy as possible while also reducing, keeping the budget down. Ask yourself, have I sized it for part load, and do I need valves on every circuit? And we'll always be happy to work with you on that and figure out what is the best approach. And if you're familiar with our Select Plus software, everything that I've done here is through Select Plus, so you can run your own utility rates, you can run your own hours, and plug all this stuff in and figure out what kind of payback you're going to get, and we're always here to help as well. So let's talk about DOAS units. Typically, a DOAS unit is a DX unit handling all ventilation air. And a common way to get you some free energy with a DOAS unit is to use hot gas reheat. Now, some DOAS units aren't DX, some are chill water, and of course, if you are using chill water, then you don't have the benefit of hot gas reheat. So the wraparound heat pipe will allow you to give you that free reheat on that dedicated outside air unit where the hot gas reheat is no longer available. But even if it is a DX unit, hot gas reheat is simply waste heat, which is not bad, but it's free reheat. We're also providing free reheat, but we're also pre-cooling to get our reheat. So we're going to offer twice as much BTU savings than a hot gas reheat would. And that has its own element of surprise, let's say, in that when you're not just getting free, you are reducing the load on your cooling coil. And when you reduce the load on your cooling coil, now you can really see the benefit of the wraparound heat pipe because you can get a smaller DOAS unit and make it more efficient. So let's look at a quick example here. Here's a 25-ton DOAS unit, and if we didn't have a heat pipe on it, let's say this 25-ton unit is going to get down to a dew point of 52 degrees off the cooling coil. It's pretty common, and if anybody wants to see any of this supporting documentation afterwards, just let me know. I'll be happy to get you any of this stuff. But this is a number I got from someone else. So let's say we put a wraparound heat pipe on it. Well, now if we need 25 tons, we don't need a 25-ton unit because the heat pipe is going to handle some of that cooling load for you. So you could get away with a 20-ton unit that has a heat pipe doing 5 more tons for you. So you got a net 25-ton unit, still getting down to that 50-degree dew point, 52, excuse me. But the key here is that, one, you just made the unit smaller. but more importantly, or just as importantly, that 5 tons is being added by using a lot less energy, which is increasing the ER. So instead of having 5 more tons of compressor working, basically adding just a little bit of static pressure to the system with the heat pipe that doesn't require any power, and that little bit of static pressure takes a lot less energy than 5 tons of compressor. And so in this case, the ER jumped up 40% all the way to 18. So not only are you going to make it smaller, which is going to make it lighter, which is going to reduce the electrical load, but it's also going to make the cost a wash, which is pretty awesome. And what do I mean by that? So yes, you pay more for the heat pipe, but the reduction in price from going from a 25-ton unit to a 20-ton unit, oftentimes that ends up being a wash. So you can tell the owner, hey, listen, you can pay the same amount, get a smaller unit, and it'll perform more efficiently than if we didn't put this on there. So it's pretty much a win-win. So some of you might be asking yourself, why don't we do this all the time? And the answer to that is pretty simple. It's that unfortunately, when it comes to DX equipment, there's not a lot of room in those units. And the wraparound heat pipe does, even though they're not that big, they do require some space. With modular air handlers and such, you know, you can create them and give the space that you need. But when it comes to, you know, set model sizes of DOAS units and makeup air units and stuff like that, there's not a lot of space. They cram it in as tight a space as possible and don't leave a lot of space for outside things like heat pipes. But also know that that's on us, and we are talking to all DOAS manufacturers. They're starting to see the value in it, so you might start seeing some changes here soon. And if you talk to some of those manufacturers or represent some of those manufacturers, to hear that from both ends would certainly help the cause. But there are things in the works that are starting to give us some more space. And on top of that, we install these wraparound heat pipes at our place as well. And some of these units we are able to modify ourselves as long as we don't have to start moving and disconnecting any piping. But we can move filter racks and stuff like that. But always send us drawings and we'll see if we can pull this off for you. So another little note on the DOAS units is typically they're decoupled and they've got some other terminal units downstream to handle the sensible load. So typically that's why you find DOAS units that are strictly there to handle humidity tend to have warmer discharge air than like a mixed air system would. And the warmer that air can be, then obviously the more reheat we can do and the more pre-cooling we're going to be able to do to get that. So the more reheat that's allowed, the better we're going to perform and the more savings you're going to get. So that's why we work very well with DOAS systems, because they tend to have a little bit more reheat associated with them anyway. Chilled beams is another cool application, and a lot of DOAS units are used to deliver the primary air for chill beam systems. So a quick summary of chill beams for those who aren't too familiar with them. They're basically diffusers out in the space that have a coil in them, and these beams will actually induce air locally across that coil to handle sensible load in the space, so that the air handlers upstream don't have to provide as much air to handle the sensible load. So the goal here is to reduce fan energy by adding a little bit of pumping energy to send water back and forth from these beams. Now the downside is that when you're providing less air, is that you have less air to dehumidify the space. So and there's the same moisture level out in the space, so that's not going to change. So the only way to battle less air is to provide drier air. So a lot of times there may not be a lot of humidity to control anyway, or you might control to a higher RH set point in the space, in which a basic, chill water or DX system can work fine, maybe with just a little bit boost on the coil side. But oftentimes there's a pressing need to go to a lower dew point to avoid that risk in providing not dry enough air, let's say. But oftentimes you'll find that the allowable dew point of that primary air can be somewhere in between, and the wraparound heat pipe is going to allow you to hit that point. It's not going to get down to those really low dew points that some of those expensive desiccant systems can get down to, but it can help the basic cooling coil drive down that dew point. What you may find is that by not only by using a less expensive solution like a wraparound heat pipe will drive down the cost in itself, but it also opens up the available manufacturers for the air handlers to be systems available that can do low dew point. And then, of course, makeup air units. VRF systems use a lot of makeup air units. Schools see them a lot. In these types of systems, again, there's something downstream that's focused on the sensible load in the space, while the makeup air unit just handles all the outside air. And again, that's a great application for the heat pipe because we're helping it pre-cool. We can shrink that system. But that extra reheat isn't as penalizing as normal systems. In hotels, we see them a lot because, especially common areas, you're providing all that pre-treated outside air, but you don't want to freeze it because there's not a lot of traffic, so that you reheat it back up anyway. So if you see any hotel applications, it's a great application for a wraparound heat pipe. Some other applications are a little off the wall. Underfloor air distribution or displacement type ventilation. Now you've got air, instead of delivering overhead, it's delivering down at your feet or your ankle area. And if that's the case, where overhead you send it out cold, because by the time it gets to the people, it's not as cold. But if you deliver it down at your feet, it's cold. So you have to deliver a little bit warmer. And again, anytime you have to control the humidity, but then reheat it back up, it's a great application for the wraparound heat pipe, and underfloor air is very much in that zone because you still have to dehumidify the space just as much, but you have to reheat the air back up. So let the wraparound heat pipe do that for you. Pool dehumidification as well. Obviously, for indoor pools, there's a lot of humidity on its own. So regardless of whether it's outside air or just recirculated air, there's a lot of humidity to control, but you don't want it to be cold. You don't want to send a bunch of cold air out to a pool area, or not a lot of people are going to swim in that pool. So you're going to want to reduce the load on that cooling coil while heating it back up. And again, perfect application for the wraparound heat pipe. Two-pipe systems, don't see a lot of those these days, but there's, for those not familiar with what I mean here, you got your two-pipe and your four-pipe system. Four-pipe means chilled water plus supply and return hot water, where two-pipe means you've only got one or the other. And oftentimes you have a changeover. So in cooling season, water, in heating season, it switches over to supply return hot water. But let's say it's cooling season, and yes, you got to control humidity. Well, you can't add hot water to it for the reheat. You can't do that anyway now because 90.1 tells you can't simultaneously heat and cool. But besides that, even if you were to try to use electric heat as reheat, that is very expensive. So the wraparound heat pipe is not only going to reduce that load like we've been talking about, but if you size it to handle that reheat for you at the small loads and add the valves to it to shave that extra unwanted reheat at the high loads, now you're getting that reheat for free while taking all that chill water from the two-pipe system. Another call that we commonly get is when final filters are wet. And you've probably heard this before, some of you have, I'm sure. Why are our final filters all soaked? Well, typically it's because it's a blow-through fan configuration, meaning that fan is not downstream of the cooling coil, it's upstream and blowing air through it and then through final filters. So what happens then is you lose the extra reheat that the fan motor adds to the system. So when the air is coming off the cooling coil, it's typically saturated, and when you add fan reheat, it pulls the air off saturation. But if it's blow-through, you don't have that extra heat. So now you have this saturated air going through these final filters, and then when it experiences the pressure drop, now that saturated air condenses to a liquid and gets your filters all soaked. So we find that simply adding a one-row wraparound heat pipe is enough reheat to pull that air off of saturation, kind of take the place of the fan heat that's no longer there, and it's going to give you a little pre-cooling while you're at it. So if you have any blow-through type configurations, always consider just a quick little one-row wraparound heat pipe to help avoid those problems. And again, we install these wraparound heat pipes in the field as well. We don't just do them at our place, and we don't just send them to the manufacturers. We'll do them out in the field. So if you have any existing jobs where final filters are getting wet, give us a call, and we'll see if there's enough space to put a small little one-row wraparound heat pipe on it and take care of that for you. And of course, I mentioned this earlier, but MRE, we're going to help improve MRE. And I'm sure most of you are asking, Drew, what is MRE? And that's an excellent question. Fortunately, I have a slide here that will answer that. So if you've been listening to us talk for the last several years, you've heard us talk about a metric called RER. And RER is strictly for energy recovery. It's the recovery efficiency ratio. So where effectiveness is measuring basically the capacity of that device or the amount of BTUs it's able to recover, RER takes into account how much power is being added to the system to go get those BTUs. So, you know, something like a wheel is getting a lot of BTUs and has a high effectiveness, but it's adding a lot of static. It's got extra air for purge, leaks. It's got a motor turning that wheel, so there's more power involved in it. A heat pipe is simply adding static pressure, so it just requires a little bit of fan energy. Well, this MRE is not to do with energy recovery. It's all about moisture removal. So there's an upcoming standard called 920 that will be coming out soon that is a standard for performance on dedicated outside air units. And within standard 920, you will find this metric called MRE, where they measure the moisture removed per the power consumed to remove that moisture. So in other words, it's the pounds of water per hour that's removed from the system for every kilowatt that's needed to go get it. So how can a wraparound heat pipe help with that? So we're going to go back to that 25-ton DOAS unit. And again, if we don't have a heat pipe on it, that 25-ton unit that gets down to 52-degree dew point, that's about 162 pounds per hour of water. And it needs about 29 kilowatts of power to remove all that moisture. So if we divided the moisture removal by the power, you get an MRE of 5.6 pounds per kilowatt hour. Now let's say we add a wraparound heat pipe to it. Now in this example, unlike the other one where we were able to shrink the unit and get the same total capacity, in this case we're going to take the same unit and add a wraparound heat pipe to it so that we're handling some sensible load so that the DOAS unit and that coil can handle more of the latent load. So what you'll find is now we're going to, instead of driving down that dew point to 52 degrees, it allows that cooling coil to drive down to a lower dew point, in this case 48 degrees. So now we've removed more moisture, and we've added very little power, because instead of, all we've done is added static pressure to the system, and not much if it's a two-row heat pipe. So it's just a little bit of fan power. So you can see that all we did was bump up the power from 29 to 29.2 kilowatts. So we increased the moisture removal by about 10%, and because that power, extra power is so small, we've actually increased the MRE by about 10% as well. So you're going to start seeing this, if you're involved with dedicated outside air units, you're going to start seeing this soon, because 920 is not out yet, but it's coming, And it's pretty apparent to us that it's known that it's coming because we've been talking to the outside air companies a lot more frequently in recent days than we have in the past. And it's all because of this MRE that they're going to be judged on. And the wraparound heat pipe is a way to boost MRE by adding very little bit of power to the system, as you can see. Finally, I just want to talk about a couple of cool case studies. One is here in Tampa. It's the Amalie Arena where the Lightning play. So several years ago, this is going to be shocking, but Tampa was known for having some of the worst ice quality in the NHL. Who would have thought? So they wanted to do something about that. So they designed this very expensive desiccant system to really dry out the air. It involved this, expensive system on the roof, gas going up to it, all kinds of good stuff. Problem was it shot their budget, and they couldn't afford it. So they tried to figure out how can they get a system they can afford and still get this dew point down. So the answer was just using basic chill water air handlers with wraparound heat pipes. So they figured they at least needed to get the dew point down to 40 degrees. So they used a couple of large chill water cooling coils in series. But then we added some two-row heat pipes around the dual cooling coils, not only that really helped pre-cool that system, but also reheat that air back up because you don't want to be sending 40-degree air out into a space full of people. So at the end of the day, they're able to get the 40-degree dew point air. They're able to now every year have the average in the NHL ice quality report, which for Tampa, Florida is a significant improvement. But also on the dollar side of the house, this is coming from them. They estimate that they save roughly $50,000 per month just on the heat pipes. So that's a pretty cool story. Another cool one that's here local in Tampa is at St. Joe's Hospital, where we have some controllable wraparound heat pipes for some OR units and IR units. And you'll typically, well, always an OR unit's going to have to be a little bit drier than normal. So they like to see those dew points down a little bit further. So again, of course, a wraparound heat pipe is a way to take a regular chill water air handler or DX air handler and drive down that dew point. But by putting control valves on it, now they're able to really control the leaving air temp coming out of these units, which is, of course, also critical for OR units. I picked some local installations here because we love to promote coming down to the factory here in Tampa, not just showing off our facility, but if you want to see some of these local installations, we got a lot of different ones. We'll be happy to give you a tour around town and show you some of these off. And for those of you that are up north and interested, if you want to wait till it gets really cold and come on down, maybe squeeze in around the golf, just give me a call. We'll set you up. Last but not least, our Select Plus design software. Hopefully everyone here has signed up for Select Plus or at least checked it out. If you haven't, all you got to do is go to heatpipe.com. There's a big logo there. You click on it, you request a user account, you create a password, and you're all set. Nothing to download, nothing to update. It's your own user abilities, and nobody's going to go see what you're doing unless you invite us. You can invite your customers, you can invite engineers, you can invite whomever whenever needed, or you can just use it to see how things are going to perform. You can get submittal drawings, and you can run all those bin analysis that I ran before. Pick a city, pick the hours, pick the days, pick the months, plug in utility rates, and see if what you're selecting is actually worth it. With that said, I would just like to mention that there is more to come in the wonderful world of heat pipes. We talked about the heat recovery side. We talked about, today we talked about the wraparound heat pipe, but we plan to have an ongoing series here, so keep an eye out in your emails. Also know for any PEs out there that PDH certificates are available. So shoot me an email or give me a call and I can set you up with one.